Assalamualaikum. Today our group will present the molecular orbital theory.
These are the members from our groups. Here, the question number 1.
For hexafluorocobaltate 3 ion, the first step to fill the electron in molecular orbital energy level is by determining the electron configuration of the metal ion and ligands. Cobalt, in its 3+ oxidation state, has an electron configuration of 3d6. Each fluoride ion brings 7 valence electrons, and since there are 6 fluoride ions, there is 42 electrons. However, since we are dealing with a 3- complex, we add 3 more electrons, totaling 45 electrons. The second step is we need to draw the molecular orbital diagram. For octahedral complex like COF6 3-, the molecular orbital diagram will have bonding and antibonding orbitals arising from the interaction between the metal d orbitals and the ligand group orbitals. Then, the third step is fill in the electrons. Start filling from the lowest energy level up following Hund's rule, Maximus multiplicity, and Pauli's exclusion principle, no more than 2 electrons per orbital with opposite spins. For the fourth step, consider the ligand field splitting. The presence of fluoride ions, which are weak field ligands, will influence the energy gap between the T2G and EG orbitals. The last step is we need to complete the diagram. Ensure that all 45 electrons are accounted for in the MO diagram, with aperiodic spins and following the energy level order. High-spin complex occurs with weak field ligands like F, where the energy gap between T2G and EG is small, so electrons occupy higher energy orbitals to minimize repulsion, more ampere electrons. Since fluoride is a weak field ligand, COF6 3- is likely to be a high-spin complex.
For the next complex compound is pentamine aqua cobalt 3 ion. For the step filling of electrons in molecular orbital, firstly we need to determine the oxidation state of metal. The central metal atom for this coordination complex is cobalt, and the ligand is NH3 and H2O. The value oxidation state for NH3 and H2O is 0. Therefore, cobalt plus 5 times 0 plus 0 equal to positive 3. Therefore, the oxidation state of cobalt is positive 3. Next, we need to find valence electron configuration of CO, which is AR3D7 4s2. For the cobalt 3 plus equal to AR3D6. Next, for bonding system, d orbital consists of 3d6. The electron contributed from metal equal to 6 electrons, and the electron contributed from ligands is 6 electrons and 2 equal to 12 electrons. So the total electron involved, which is metal plus ligand, equal to 18 electrons. Strong field ligands typically lead to a large splitting energy, which favors a low spin configuration where the electrons are distributed to minimize the number of ampere spins. Hence, cobalt 3 has no ampere electrons due to the high spin nature of complex. This means the electrons are paired in the lower energy T2G set. Therefore, it is diamagnetic and low spin complex.
Next, I will explain the state of filled electrons in the molecular orbital energy level diagram for trichlorotriamine cobalt 3. From the coordination complex, the metal center was cobalt and the ligands were NH3 and Cl-. So, firstly, we need to determine the oxidation state of metal center. The oxidation state obtained for cobalt ion is +3. The second step is to determine the valence electron configuration of cobalt. The valence electron configuration for the cobalt ion in this oxidation state, cobalt 3+ is Ar3d6. Thirdly, the d orbital system for bonding was determined to be 3d6. Next, we need to determine how many electrons were contributed from metal and ligands. There were 6 electrons contributed from cobalt, while the electrons contributed from ligand were 12 electrons. Therefore, the total number of electrons involved was 18 electrons. Since both neutral ligands and weak field ligands are present in the complex compound, NH3 is the neutral ligand and Cl- is the weak field ligand. The weak field ligand will decrease the splitting energy, which will result in the coordination complex being a high spin complex with 4 unpaired electrons.
So next, we will discuss about MoCO6, which is molybdenum hexacarbonyl, and we have 6 steps for filling electrons of MO. The first one, we have to determine oxidation state of metal, which is no oxidation number. Number 2, valence electron configuration of MO, which is 5s1 and 4d5. The orbital system for bonding is 4d5. Electron contributed from metal is 6 electron. Electron contributed from ligand is 12 electron, and total electron involved, which is M plus L, is 18 electron. So here, this is the MO energy level diagram for MoCO6. MoCO6 is a low spin. This is because the strong field ligand CO causes a large crystal field splitting, making the energy difference between the T2G and EG orbitals significant. As a result, the single electron in the 4d orbitals of MO6 plus will occupy one of the EG orbitals high energy, leading to a low spin configuration, where there is a minimal pairing of electrons in the lower energy orbitals T2G, and there are no unpaired electrons. So here, we will discuss about MLCT transition. The first one, transition that the electronic charge shift from the molecular orbital with a metal-like character to the ligand-like one. Number 2, occurs when the ligand contains unoccupied pi star orbital, example CO or Cr-, and the metal is in a low oxidation state, electron rich. And the last one, this causes the metal to get oxidized. Example of the MLCT transition is the tris-bipyridine ruthenium-2 RuBpY32+. So here is the MO energy level diagram of the compound.
Tris-bipyridine ruthenium-2 is a prime example of a metal to ligand charge transfer MLCT complex used in catalysis applications, particularly in photoredox catalysis. Photoredox catalysis involves the use of light to drive redox reactions through the generation of reactive excited states of photocatalysts. Tris-bipyridine ruthenium-2 can act as a photocatalyst for the splitting of water into oxygen and hydrogen gas. Upon absorbing light, the excited state of tris-bipyridine ruthenium-2 initiates electron transfer process that lead to the reduction of protons H+ to form H2, a clean and renewable fuel. Meanwhile, in organic photocatalysis, tris-bipyridine ruthenium-2 can participate in oxidative or reductive process. For example, it can oxidize organic substrates by transferring high-energy electrons to initiate chemical reactions that are otherwise difficult under normal conditions.
Next, question number 3. Ligand to metal charge transfer. Ligand to metal charge transfer (LMCT) transition involves the migration of electrons from filled ligand orbitals, typically pi orbitals, to vacant metal orbital in metal complexes. These transitions are characterized by several key features. The metal center must possess high energy vacant orbitals and be in high oxidation state, while the ligand should have low energy filled orbitals to facilitate electron transfer. LMCT transition can occur in complexes with metal from various groups, including main group transition and inner transition metal. During an LMCT transition, an internal oxidation of ligand and an internal reduction of metal take place. Here the example of catalysis process using LMCT metal transition. Here the process divided by 3 sections, which is experimental process, absorption and excited state process, and lastly is photochemical process. The process starts by dissolving potassium ferrioxide in an acidic solution and exposing it to the light, which induces an electron transfer from the oxidate ligand to the ion center. This leads to the formation of an unstable oxidate radical anion, which dissociates into carbon dioxide. Next, another ferrioxide molecule then treated with excess phenylenedione in acetate buffer to form molecule combination of ferrous and phenylenedione, whose absorption profile is easier to analyze. The chemical reactivity of potassium ferrioxide make it ideal compound for actinometry, offering a reliable method to measure photon flows and quantum yields in various light-induced chemical processes. That's all from our group. Thank you.